Hello everyone. What we'd like to do in Chapter 4 is discover or play around with two incredibly important functions in mathematics. Not just mathematics, but also in science. We're going to be exploring something called the exponential function, and then we're going to be talking about its inverse function, which is a logarithm. So we've already been talking about functions, we've been talking about their inverses. What we're going to be paying attention to a lot in Chapter 4 is a specific flavor of function, an exponential function, and its inverse, the logarithmic function. So let's begin. I can't stress enough the importance of this chapter, the importance of exponential functions, the importance of logarithmic functions. They pop up everywhere. I know a lot of students really struggle with exponential functions and logarithms, so make sure just to take your time in this section, really try to absorb the material, so when you see this stuff pop up in future math classes, you'll feel very confident. Okay, so let's talk about what an exponential function is. Okay, so what I'd like to do here is hopefully give you an example. So how about a fun example? Let's do an example of zombies. So let's say there's some sort of zombie outbreak. Okay, let's say these are the conditions of the outbreak. So let's say it starts with one zombie. Start with one zombie. And let's say it increases by, let's say, 100% each day. So what I mean by increasing by 100% each day is you start out with one zombie, the next day there will be two zombies, the next day there will be four zombies, so the population increases by 100% each day. Okay, so let's go ahead and try to build a model for the zombie outbreak. We're worried, zombies are everywhere, we want to know how long do we have to live. So us as scientists, we want to figure out, is there a nice model where we can predict, really, I guess, how long do we have, I guess, maybe to survive. So let's make a function, let's make a table of what's going to happen. So let's say here we have time. We'll use the letter T for time, and in this case, time will be in days. So this will be days. And what we'll write here is the zombie population. The zombie population. Okay. So let's start at time t equals 0. So this means, I guess, on day 0 when it initially outbreaks. So how many zombies are in day 0? Well, we are starting with one zombie. So when the outbreak begins, there's one zombie. Okay, let's think about what's going to happen. Well, on the next day, the population is going to increase by 100%. This just really means that the population is going to double. So we're going to take this 1 and we're going to multiply it by a 2, so we're going to get out 2 zombies. Okay. Similarly, let's say on the second day, what's going to happen? Well, the population's going to double again. So we started with 2 zombies, and now this is going to double. So now we're going to get 4 zombies. But how about I write this as 2? We multiply 2 by itself twice. We're going to get out 4 zombies. Similarly, on the third day, what's going to happen? Well, we have 4 zombies, or what we can think here is we had 2 times 2 zombies. Well, that's going to double again. So we'll have 2 to the third power, which will be equal to 8. So notice I'm basically just taking 4 and doubling it. I'm writing it this way for a certain reason. We could continue doing this. I hope what we see is a nice pattern. So what we want to know is what's going to happen after t days. Well, looking at this pattern, for kind of thinking, this is 2 to the first power, this is 2 squared, this is 2 cubed. So if I want to know how many zombies there are after t days, it seems like what we're doing is we're just taking 2 and we're raising it to the tth power. So after 4 days, there would be 2 to the 4th zombies. After 10 days, there would be 2 to the 10th zombies. So now what we have is we have a nice function which will tell us how many zombies there are after a certain number of days. Let's call this z of t. Zombies as a function of time, and this is 2 to the t. Okay, so this is saying that every day the population is going to double. Okay, so how long do we have to live? Let's play around with this. So let's see. So after 3 days, there's 8 zombies. Maybe we're not too worried, but I don't know. Let's say what's gonna happen. What's gonna happen after a week? So that's 7 days. So what happens after 7 days? So this is 2 to the 7th. So let's see what we get here. Okay, what's 2 to the 7th? That's 128 zombies. Okay, so maybe you're not too worried right now. There's only 128 zombies. Okay, well, how about maybe after 2 weeks? Maybe, so that'd be 14 days. What's 2 to the 14th? So 2 to the power of 14. So if you don't know how I'm computing this, I'm putting 2, and then there's this caret symbol here on your calculator. So 2 to the power of 14. We'll go ahead and hit enter. So it looks like, oh my goodness. Now, after a week, we have 128 zombies, but after 2 weeks, holy cow, there's 16,384 zombies. Ooh, oh man, getting a little nervous, getting a little scared. Well, maybe we want to know, maybe how long do we have to live? But maybe here in Bellingham, what's the population of Bellingham? Population of Bellingham. Okay, the population of Bellingham, my notes tell me it's roughly 80,000. So we also have a population of 80,000. So how long till Bellingham gets overrun? So what we'd essentially want to solve here is we'd want to know, well, what value of t would we plug in to get an output of 80,000? This is an example of something we'll call an exponential equation. We don't have the tools right now to be able to solve this for t. We will soon, once we get the idea of what a logarithmic function is. But let's just kind of guess and check here. So there's 2 to the 14th. Okay, well, what if we do 2 to the, what about after 3 weeks? Oh man, that's no good news. It's no good news. We won't even have 3 weeks. Z of 21 after 21 days. 2 to the 21st power is 2097152. So, oh my goodness. After 3 weeks, it already looks like there's 2 million zombies. Ugh. So we're not even going to make it. We're not even going to make it 3 weeks. Okay. I don't know. We could, when we did 14, how about after I don't know, how about after 15 days? So 2 to the 15th. Or let's do 2 to the 16th. How about 2 to the 16th? What happens after 16 days? So we get 2 to the 16th. 2 to the 16th. We get 65,536. How about we do 2 to the 17th? We could just multiply this answer by another 2, but sorry, my board's getting so I don't know, messy. But z of 17, what's 2 to the 17th? Well, 2 to the 17th is 131,072. So, man, we got between 16 and 17 days before Bellingham is going to get overrun by these zombies. Okay, so what we should kind of notice with this type of function, something of this form, 2 to the t, this is an example of something that's called an exponential function. And the thing to think about exponential functions is that they grow really, really, really quickly. So, even 2 to the 7th was 128, but 7 days later, or, if I change my input by 7, now I'm at 16,000 roughly. If I change my input, by another 7, now I'm at 2 million. Look how fast this function here is growing. This is a lot of how population grows, and we have to be careful. Things can grow really quickly, and especially when we're thinking about the whole COVID thing that's going on right now, things grow exponentially. One person gets it, then another person gets it, now 2 people have it, then 4 people have it, then 8 people have it. It's going to grow really, really, really quickly. So this is an example of an exponential function. Okay, and this is the type of things we want to study. They have a lot of applications, specifically in population, as was one of the biggest applications. Okay, so let's talk about exponential functions a little bit more generally. Okay, so examples of an exponential function. Examples of exponential functions. So we could have f of x could be equal to 2 to the x. We used t for time, but we could have f of x be 2 to the x. We could have another function that we call a g of x, and maybe it's 10 to the x. And let's say we have another one, let's say h of x, and let's say this is 2/3 to the power of x. Okay, so these are all examples of exponential functions, and we have names we give to the certain pieces. So the 2 right here is what we call the base. So this is the base of the exponential. The base here is 2. Similarly over here we would have a base of 10. Base 10, this is a base 10 exponential. Over here, we can have a fraction as a base. Here, the base is 2/3. So the number that's being raised to a power is what we call the base. And, maybe in red, what we call what it's being raised to, so let's say here, the x values here, these are all called the exponent. These are all called the exponent. So there's the base and there's the exponent. Okay. So let's talk about a little bit more general about this. So here are just some examples, but in general, let's say in general, right here, in general, an exponential function always has the form f of x is equal to b to the x. B is the base. So this b here is the base. And the x we call the exponent. Okay. We want to talk about this a little bit more, though, because it turns out that we only really care about specific bases b. There are conditions on b that we need to make to be able to get an exponential function. Okay, so what should be the conditions on b? Well, let's talk about some really boring cases first. So what would be like a really boring base, like a super yawn fest? Well, for example, what if b was 0? So, kind of thinking about it, or what if b was 0 here for a second? Well, then my function, f of x, would be what, 0 to the x? So, but 0 multiplied by itself any number of times is still just 0. So if the base was 0, we're not even getting something that grows really quickly. We don't really have a nice exponential function. If b is 0, we just have the equation f of x is equals to 0. That's just the x-axis. Any value of x you plug in, you're just going to get an output of 0. This is a yawn fest. This is exponential functions. We want them to behave like something that grows pretty quickly. So having a base of 0 is not of much interest. It's too boring. So for exponential functions, we make the condition that the base cannot be 0. Okay, how about something else? What else would be a super yawn fest? Well, what if b was 1? That would be a super yawn fest too. If b was 1, then we'd have that f of x would be equal to 1 to the x, but 1 raised to any power, 1 to the 1 cubed, 1 times 1 times 1 is 1. 1 times itself any number of times is still just 1. This would be 1. Again, this is just a horizontal line, y equals 1. This is a yawn fest. Any value of x I plug in, we're just going to get the same output of 1. This is a linear equation. This isn't something that's an exponential equation. So we also are going to make the condition that b can't be 1. Super yawn fest. So these are the conditions here. Too boring. Too boring. We don't care about these. Okay, there's another thing that we should think about. Now let's think about too interesting. Too interesting. Okay, we also have the condition that we want b to be positive. So what we want here is we actually want b to be positive also. Okay, notice here when I'm saying that b is strictly bigger than 0, I'm also taking into account that b cannot be 0. So I'm actually going to erase that b can't be 0, and we're actually going to make a stronger condition that's saying that b has to be positive. Okay, why? Well, if b is negative, it's too interesting. The graph kind of turns out to go all over the place. So for example, let's say even if the base was, well, let's just do -2, for example. What if the base was -2? -2 to the x. Okay. What if we had a function like this? Well, what happens? Well, let's say we plug in 1. If we input 1, we're going to get a -2 to the first power, which is -2. Well, what happens if we plug in 2 now? Then we get -2 squared. -2 squared, -2 times -2 is 4. Okay, and if we plug in 3, then we're going to get a -2 cubed. -2 times -2 is +4. +4 times another -2 is -8. So notice what's happening here is actually the function is kind of jumping between being positive and negative. For any odd input, and a negative number to an odd power spits out something negative. A negative number raised to an even power is going to spit out something positive. So in this case here, when I'm inputting things into a function that has a negative base, it's going to be positive, negative, positive, negative, positive, negative. It's going to be jumping all over the place. It's too crazy. We want a nice smooth graph that kind of says how a population might be growing. So in this case, having a negative base, too interesting. It's too crazy, and it's not really modeling what we want it to model. We want it to model things like population growth, or we'll see here soon, money in a bank account. You have money in a bank account, it earns interest, and you have more money, and that more money is going to be gaining interest. Your money will be growing exponentially. This having a negative base, it's too crazy, it's all over the place, too interesting, and so for that case, when we talk about exponential functions, we're only going to consider cases when b is positive. So, this is something we really need to hold on to, something we need to remember. When we're talking about exponential functions, an exponential function is something of the form b to the x. We call b the base. The x is what we call the exponent. We have conditions on b. b needs to be positive, and b cannot be 1. So we need to hold on to this idea. Okay, now we're going to be graphing these here pretty soon. But what I would like to point out is for every single exponential function, I would call this a non-transformed exponential function. So maybe I should write this. So I would almost like to call this, kind of loosely speaking, this is kind of our toolkit. Our toolkit exponential. Our toolkit exponential. Now the graph will look different for different b's, but we're gonna, for different bases, we'll have a certain graph, and then we can take that graph, we can shift it up and down, we can shift it left and right, we can stretch it, we can compress it. But for right now, when we have just something of the form b to the x, we'll call this kind of the toolkit exponential, and then we're going to think about transforming them soon. But what we want to do, and what we want to hold on to an exponential function, is every exponential function of this form has 2 special points we're going to want to pay attention to. So I'm going to write down here key points, and we're going to be coming back to this, I promise. Key points. What are some nice key points that will always be on this function? Well, for example, let's start with evaluating this function here at 0. Notice that if we do f of 0, I'm evaluating my function at 0, this would be b to the 0th power. Now we need you to remember that any number raised to the 0th power will always be 1, so this will be 1. So for every exponential function, we'll always have 1 point, or we'll always have this point on its graph. Every exponential function of this form will always have the point 0 and 1 on the graph. It'll always be there. We need to hold on to that. Another key point that we're going to want to pay attention to is not just plugging in 0. Another good number to input into the function is 1. So if you plug in 1, for example, you'll get b to the first power, anything raised to the first power is just itself b. So the point 0, 1 will always be on the graph, and also the point 1 and b will also be on the graph. Let's hold on to these. These are going to be key points that we're always going to want to be paying attention to, specifically when we start transforming these functions. Okay, so we haven't actually even looked at a picture of a graph of an exponential function, so let's go ahead and do that, and then we're going to be doing lots of examples about how to graph transformed exponential functions. Okay, I'm going to go ahead and erase this. Okay, so let's just kind of work with some inputs and outputs of some exponential functions. Let's get a feel for what they look like. Okay. Let's graph two different ones. So, graphing exponentials. Okay, so when we're graphing an exponential, what we're going to do here first, and what we're going to want to get away from, is whenever you're trying to figure out what a graph of a function looks like, first, we're going to make a t-table. We're going to make a table of inputs and outputs. We're going to plot them. We're going to do this really old school, kind of, really brute force what these graphs look like. And then once we get a feel for their general shape, then we'll just think about transforming them. We're kind of shifting them, stretching them, reflecting them. Okay, let's look at two nice examples here. So the first one we're going to graph is let's graph f of x, which is equal to how about 2 to the x. Okay. Let's graph another function. So here I have a base of 2. I have a base bigger than 1. So repeatedly multiplying 2 by itself. But another good function we should think about is what if the base is a fraction? So let's also look at, how we call it g of x. Another function, g of x. Let's see what it would look like if we have 1/2 to the power of x. Okay, we're going to make a t-table and we're going to plot a bunch of points here. Okay, so let's do it. We're going to want a good amount of room. Try not to get in the way. Okay, so here are some x values. Let's figure out what 2 to the x would look like. And we'll also figure out what 1/2 to the x looks like. Okay, so let's first start by plugging in positive numbers. So those are the easiest ones to think about. So we could plug in, I don't know, how about we plug in 3, or let's plug in 3, 2, 1, and 0. Let's start here. Okay. So here, when I input 3 in for x, I'm going to get 2 cubed. So 2 cubed, I hope you believe, is 8. We'll also have 2 squared, I hope you believe, will be 4. 2 to the first power, I hope you believe, will be 2. Notice the point, I'll hold off on a second. And then 2 to the 0, anything to the 0th power is 1. Notice here that the point 0 and 1 is on this graph, and also the point 1 and b would be on the graph, or 1 and its base is on the graph. Okay. Similarly, if I want to write, if I want to do it for the one that's a fraction, so if I have 1/2 cubed, so notice what this means. This means 1/2 times 1/2 times 1/2. So this will be 1/2 times 1/2, which is a 1/4, times another 1/2, which will be an 1/8. So I'm multiplying 1/2 by itself 3 times, and we should get out 1/8. Similarly, if I do 1/2 squared, I hope you believe this will be 1/2 times 1/2. 1/2 of 1/2 is a 1/4. Okay. And if I want to do 1/2 to the first power, I'm multiplying, 1/2, I don't know, anything to the first power is just itself. It means there's just like 1/1/2 there. This means there's like 2 1/2, so 1/2 times 1/2. This would just be 1/2. And then we would have a 1/2 to the 0th power, and anything to the 0th power will be 1. Okay. Let's make a note and kind of pause here really quick on these two examples here. For this first one, when I have 2 to the power of x, I'm repeatedly multiplying 2 by itself. Notice that the numbers are getting bigger when I input bigger values. I started out with 1, then I got 2, then I got 4, then I got 8. Over here, you could think of almost this, you could almost think that this is like exponential growth. Things are getting bigger. You started with 1, then you get 2, then you get 4, then you get 8. Things are doubling. Over here, we might call this exponential decay because the numbers are getting smaller. Think that we started with a 100% population, and now the population is halving each time. So you started with 1, and the population gets halved. Then the population gets halved again. Then the population gets halved again. So here, the graph is getting smaller. We might call this exponential decay. Sometimes we might call this half time. Okay, so hopefully this makes sense so far. But what we want to do here is, what if we were to plug in negative values? So let's think about what negative values would mean. So let's go ahead and plug in -1, -2, -3. I'm sure -3 should be enough. Okay, so there's something we need to remember about how negative exponents work. So, I guess recall that if I have any number, let's say 3, well, this is how I think about it. So when I take the number 3 and then I square it, I think about when I raise it to the power of 2, this means I'm repeatedly multiplying 3 by itself. So this is 3 times 3. Okay, what would it mean when I say 3 to the -2? I interpret negative exponents not as repeated multiplication, but repeated division. So really what this means is that take, 1/3 and multiply it by itself twice. So when you're thinking about dividing by 3 is the same as multiplying by 1/3. So it's like I'm kind of dividing by 3 twice. That's how you should interpret this negative exponent. Okay, so in general, if we have a number b and we raise it to the -nth power, this is the same thing as, I guess this would almost be the same thing as 1/3 squared. So b to the -n means 1/b to the n. So negative exponents is saying I'm dividing by b n times. Negative exponents means repeated division. Positive exponents means repeated multiplication. That's how I interpret it. Okay, so for example, if I want to know what is 2 to the -1 power, this says divide by 2 once. So this is 1/2. So 2 to the -1st power is 1/2. Similarly, 2 to the -2 power, this says divide by 2 twice. So this is 1/4. So 2 to the -2 is 1/4. Okay. If we do 2 to the -3, this says divide by 2 3 times. So this will be 1/8. So here we get 2 to the -3 is 1/8. Okay. Let's see what happens when we plug in negative exponents. Negative exponents when we have a fractional base. Okay, so let's say we do 1/2. Well, 1/2 to the -1 power. Okay, so what does this mean? One way to think about this is saying divide by 1/2 one time. So what this is basically saying is when you're dividing by 1/2, you want to know how many times, in this case, how many times does 1/2 go into a whole? I hope you believe that 2 halves make a whole, so this is just 2. Or if you want to think about this as 1/1 divided by 1/2, remember how we divide fractions? So 1/2 divided by 1/2, this is 1/2 times, 1/1 times 2/1, so this is 2. So either way you want to think about it. Okay, so we have that. So we have that 1, we do it in blue. We have that 1/2 to the -1st power is 2. Similarly, if we did 1/2 to the -2 power, this says divide by 1/2 twice. So this is 1/1/2 squared is 1/4. And this, how many times does 1/4 go into a whole? How many quarters are in $1? 4. Or you could think about reflecting the 1/4 and multiplying it into the 1. So 1/2 to the -2 is 4. So here we have 1/2 to the -2 is 4. And similarly, we have 1/2 to the -3, I hope you will believe, is 8. Okay, we have these points here. Now let's plot them. Okay, we're really brute forcing to figure out what these graphs look like. This is how every great math research problem works. I don't really know what these look like, so we're just going to plug in a couple values and see what it outputs. Okay, we won't have to do this in the future. So let's go ahead and sketch these. Okay, so let's mark our points. So what do I have to go up? I have to go up to 8. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. So let's say this is 8 right here. Okay, so for 2 to the x, okay, if we plug in 0, we get an output of 1. Or I guess if we plug in 3, we get an output of 8. So if I plug in 3, we get an output of 8. Okay, if we plug in 2, we get an output of 4. Here's 4. If we plug in 2, we get an output of 4. And if we plug in 1, we get an output of 2. 1, we get an output of 2. And if we plug in 0, we get an output of 1. If we plug in 0, we get an output of 1. Okay. So here's a 1. Okay, if we plug in -1, we get out a half, so here's a half. If we plug in -2, we get a fourth, so now I'm getting even closer to the x-axis. And if I plug in -3, I'm going to get something even closer to the x-axis. So let's see what's happening here. For 2 to the x, for positive numbers, it's getting really large. It's getting really large. And when we're plugging in negative values, it's getting really small. So if we plugged in -4, we'd be at 1/16. And if we plugged in -5, we'd be at 1/32. So what we should notice here, right off the bat, is that this exponential function has a horizontal asymptote. So let's write that. We have this horizontal asymptote at y = 0. Okay, let's see what the graph, and notice here I kind of said a second ago that this kind of models exponential growth. As x is getting bigger, 2 to the x is getting bigger. I would like to write this down. What we should be noticing here is that as x is getting really large, well, 2 to the x is getting really large. Similarly, as x is going towards -infinity, when I start to plug in negative values, 2 to the x is approaching the horizontal asymptote y = 0. So 2 to the x is getting arbitrarily close to 0. Notice though it's getting arbitrarily close to 0 from a specific side of the x-axis. It's getting closer to 0 from the top, from the positive side. So we put a 0 and we put a little plus here. This is saying that there is a horizontal asymptote, kind of right here. This specifically is saying that there is a horizontal asymptote. At the line y = 0. There's a horizontal asymptote at y = 0. Okay, now let's go ahead and graph the blue one. Okay, so this is 1/2 to the x. So now when we plug in 3, we get out something really small. We get out an 1/8. When we plug in 2, we get out a 1/4. So a little bit higher. When we plug in 1, when we plug in 1, we get out a 1/2. And when we plug in 0, we get out. When we plug in 0, we get out 1. Not surprising. All simple exponential functions, anything b to the x, will always have the point 0, 1 on it. If we plug in -1, we get out 2. If we plug in -2, we get out 4. If we plug in -3, we get out 8. So we have the graph of 1/2 to the x. Let's write this. This is 1/2 to the power of x. This is 2 to the x. I don't have to put parentheses for this one. This is 2 to the x. These graphs look very familiar. They look, I'll talk about this a little bit more in a second, but they look like they're reflections over one another over the line, over the y-axis. Before I go on to explore that idea here, notice though, for 1/2 to the x here, 1/2 to the x, that it's decaying. We have exponential decay. The larger values you plug in, the smaller they're getting. This should make sense because I'm repeatedly multiplying by 1/2. I'm taking a quantity, I'm halving it, then I'm having it again, then I'm having it again, then I'm having it again. And just keep doing that. Okay, so if we're trying to understand the behavior for 1/2 to the x, we should notice that as x is getting really large, we have that 1/2 to the x is getting closer to 0. Specifically 0 from the positive side. Also, as x is getting closer towards negative infinity, 1/2 to the x is exploding. It's going towards infinity. And we should also notice that it also has that same horizontal asymptote. It turns out that all exponential functions of the form b to the x will always have a horizontal asymptote at y equals 0. This is a property of an exponential function. So let's kind of write down some key things here that we've noticed. Okay, I'm gonna erase this right here. Okay. So I'm gonna say, notice 2 to the x and 1/2 to the x look like reflections about the y-axis. Maybe take a moment and think about why this is true in terms of transformations. Okay, this comes down, this is actually not too much of a surprise, because notice you can write 1/2. 1/2 is equivalent to 2 to the negative first power. So, when I'm thinking about 1/2 to the x, this is equivalent to 2 to the negative 1 to the power of x. And notice, or we should remember an exponent rule, that whenever we have x to the n to the m, this is the same thing as x to the n times m. So these multiply together, so this is the same thing as 2 to the negative 1 times x, or this is just 2 to the negative x. So 1/2 to the x is the same as 2 to the negative x. Oh my goodness! Oh my goodness, this is a reflection. Reflection over the y-axis if we're thinking about in terms of transformations. Here if I have 2 to the x, all my x values are positive, but, well, you know, if I'm thinking about the positive side, think about all our positive x values. If they were positive, now I'm making them negative. When you throw a negative on the x value, that takes all your x value, and now that makes them negative. It's going to reflect over the line, over the y-axis. You're taking the x values, they were positive, and now you're making them negative. Or the negative values, they used to be negative, and now they're positive. So it's no surprise when we saw 1/2 to the x that it really is just a reflection over the line or over the y-axis. Okay, let's do a recap of everything we've learned in this video. So what we've learned is that an exponential function has the form b to the x. B we call the base, x we call the exponent. Now there's conditions on the base. We have that the base has to be greater than 0 and that the base cannot be 1. Now, depending the graph of the function of an exponential depends on the value of b. So, in the case where b is greater than 1, b is greater than 1, then we get an exponential growth model. The graph will be growing. Now, this should make sense. For example, if we have 2 to the x, and repeatedly multiplying 2 by itself, those outputs should be getting larger and larger. So this is called exponential growth. exponential growth. Okay? If b is a fraction, something between 0 and 1, then we get exponential decay. So this is exponential decay. Okay. And this should also make sense, because if our base is, let's say, 1/2, for example, I'm taking 1/2 and I'm repeatedly multiplying itself. If I take a half of a half, that's a fourth, another half of a fourth is an eighth, the outputs should be getting smaller. This is an exponential decay model. Okay. Some other things we should hold on to are the domain and range of these functions. So notice for both of them, the domain, well, notice we can plug anything we would like into the function. The domain of an exponential is from -infinity to infinity. Any number, any real number we plug in, will always get a real output. Okay. And then the range, well, notice here I can only get outputs strictly bigger than 0 for both of these pictures, so the range will be from 0 to infinity. Okay. These graphs also have a nice feature on them. They have a vertical asymptote. They have a horizontal asymptote at y equals 0. They have a horizontal asymptote at y equals 0. They also have 2 key points we'll want to keep track of. So I'll kind of write key points. Key points. The key points that are on any exponential of the form b to the x. Well, if you plug in 0, you're always going to get an output of 1. And if you plug in 1, you're always going to get an output of b. So here we are. These are the key things that we need to remember about exponential functions. In the next video, what we're going to do is we're going to be taking these exponential functions and we're going to transform them. We'll see you there. Take care.